design of Dhalin's controller. For Gp of s equal to e power minus 1.346 upon 3s plus 1. 3s plus 1. For this, we have to design a Dhalin controller. Already we know that the Dhalin controller is d of z equal to 1 by h gp of z, y of z upon y set point of z, whole divided by 1 minus y of z upon y set point of z. This is for any digital controller, this is the formula. But for Dhalin controller, we are assuming that it is a response, it is also a first order response with dead time. Here, this dead time, we are assuming that k equal to 2. Here we are assuming that dead time equal to 2 sampling period. Why? Because the dead time is 1.346. Because sampling period t equal to 1 second. Therefore, it is greater than 1 sampling period. That's why we are assuming that k equal to 2. The dead time is k equal to 2 seconds. We are assuming. Because it is the dead time is greater than 1 sampling period. That's why we are assuming that k equal to 2. Therefore, y of s equal to, this is the response, y of t. This is y of t for step input. This is for step input. Y set point of z, y set point of is s equal to y set point of s equal to 1 by s, step input. This is the response. Response means it is a transfer function. So y of s equal to g of s multiplied by r of s. This is the response. G of s is the response, is the g of s multiplied by r of s. That g of s is first order with dead time. Let us assume that it is e power minus 2s upon 2s plus 1. The closed loop time constant is less than open loop time constant. Open loop time constant is slow process. We can make it fast in closed loop. That is possible. That's why we are selecting 2s plus 1. The response is, the time constant of the response is 2s plus 1 with a dead time of 2 seconds. That is our assumption. Y of s equal to e power minus 2s upon 2s plus 1. Y set point of s equal to 1 by s. Therefore, multiplied by g of s is this. So g of s multiplied by r of s, that is 1 by s. For this, we have to find y of z. Y of z equal to e power minus 2s means z power minus 2. For this, z transform of 1 upon s multiplied by 2s plus 1. That is equal to I'll write the expression directly. Okay. If you this is equal to z power minus k, we can write. If you write expression for this general system Z transform of 1 upon S multiplied by tau S plus 1. Let us first write generalized Z power minus K. For this, what you will get is 1 upon 1 minus Z power minus 1 multiplied by 1 minus e power minus t by tau. T is a sampling period. T by tau Z power minus 1. Here you will get 1 minus e power minus t by tau Z power minus 1. If you substitute, this is y of z. Y set point of z equal to what? Y set point of z equal to, for 1 by s, if you take z transform, you will get 1 minus z power minus 1. Therefore, y of z divided by y set point of z equal to this 1 minus z power minus 1 getting cancelled. Therefore, you will get z power minus k minus 1. How this minus 1 comes? Because of this z power minus 1. If you combine these two, you will get z power minus k minus 1. 1 minus e power minus t by tau whole divided by 1 minus e power minus t by tau z power minus 1. What is d of z? D of z equal to 1 by hgp of z, y of z by y set point of z. If you substitute this here, what you will get is d of z equal to 1 by hgp of z. If you substitute that, what you will get is, what is it? Y of z by y set point of z? 1 minus e power minus t by tau z power minus k minus 1 divided by 1 minus e power minus t by tau z power minus 1. One minus z power minus k minus 1, 1 minus e power minus t by tau divided by 1 minus e power minus t by tau z power minus 1. Therefore, d of z equal to 1 by hgp of z. If you take LCM, these two getting cancelled. If you take LCM, these two getting cancelled, and this part will come here. Therefore, we can write 1 minus e power minus t by tau multiplied by z power minus k minus 1 whole divided by 1 minus e power minus t by tau z power minus 1 minus z power minus k minus 1, 1 minus e power t by tau, t by tau. This is the controller for d of z. This is the controller for d of z. Now we have to find the controller. Now this is the controller for Dhalin's controller for given process. What is the given process? The given process is GP of S. GP of S equal to e power minus 1.346 upon 3s plus 1. H of S equal to what? The whole circuit is 1 minus e power minus s upon a sampling period equal to 1 means you get this 1 minus e power minus s upon s. Therefore, H GP of s equal to 1 minus e power minus s upon s multiplied by e power minus 1.346 upon 3s plus 1. That is equal to 1 minus z power minus 1. If you take z transform, HGP of z equal to HGP of z equal to, for this part you will get As sampling period is 1, you will get 1 minus z power minus 1. This can be separated in two parts. This is greater than sampling period. That's why you can this can be separated in two parts. One is e power minus 1s and e power minus 0.346s. Like that, you can separate. For this, the z transform is z power minus 1. And the remaining part is z modified because it has a dead time. That's why z modified of e power minus 0.346s upon s multiplied by 3s plus 1. This we have to find. If you find that modified z transform, the general formula I will tell, then I will write the expression. Z modified z transform of e power minus theta s upon tau s plus 1 multiplied by s equal to z power minus 1 upon 1 minus z power minus 1 minus e power minus m by tau whole divided by 1 minus e power minus 1 by tau z power minus 1. Z power minus 1, where m equal to where m small m equal to 1 minus theta by tau. Theta by t. T is the sampling period. Therefore, 1 minus, in this case, t equal to 1, 0.346. That is equal to 0.66. 0.66. You will get 0.66 is the m. So if you find, then HGP of z equal to, by using that modified z transform, by using this formula, if you find z transform for HGP of s, you will get HGP of z equal to 0.0876 z power minus 3 plus 0.1959 z power minus 2 upon 1 minus 0.7165 z power minus 1. This is HGP of z. Therefore, d of z equal to you have to write 1 by HGP of z. Therefore, 1 minus 0.7165 z power minus 1 upon 0.0876 z power minus 3 plus 0.1959 z power minus 2. We will get, this is for 1 by HGP of z. Now we have to write e power, what is d of z? 1 minus e power 1 by tau. Here tau equal to, we are assuming 2. Z power minus k minus 1. Therefore, z power minus 3. If you e power minus 1 by 2, that is 0.6321 whole divided by 1 minus 0.3679 z power minus 1 minus 0.6321 z power minus 3. If you simplify this, you will get d of z. D of z equal to 0.6321 z power minus 3 minus 0.4529 z power minus 4 whole divided by 0.0155 z power minus 3 minus 0.0322 z power minus 4 minus 0.0554 z power minus 6 plus 0.1959 z power minus 2 minus 0.1238 z power minus 5. The highest power is z power minus 6. To make it all positive powers, multiply the numerator denominator by z power 6. Therefore, you will get 0.6321 z power 3 minus 0.4529 z square. Multiply the numerator denominator by z power 6. You will get 0.1959 z power 4 plus 0.0155 z power 3 plus minus 0.0322 z square minus 0.1238 z minus 0.0554. This is the controller. We are assuming that the mu equal to 1. We assumed that mu equal to 1. Sorry, mu equal to 1 we assume. Here we have to assume the closed loop time constant. We have to assume closed loop time constant that I said 2, you know. This is the expression for mu equal to 1. This is for mu equal to 1. This is for mu equal to 1. This is for mu equal to 1. So we are assuming that the closed loop time constant is 1. If you assume mu equal to 2, we will get the final expression I will write. The final, if you assume the closed loop time constant mu equal to 2 means d of z equal to 0.3935 z cube minus 0.2819 z square upon 0.1959 z power 4 minus 0.0312 z cube minus 0.0531 z square minus 0.0771 z minus 0.0345. That is constant term. This is the controller if mu equal to 2. If you assume mu equal to 3, you will get the controller. I derived, but you can check yourself. Mu equal to 3, you will get 0.2835 z cube minus 0.2031 z square upon d of z. D of z equal 0.1959 z power 4 minus 0.0528 z cube minus 0.0628 z square minus 0.0555 z minus 0.0248. This is the controller. So we are assuming different time constants. If you reduce the time constant, the response will be very fast. What is the meaning of time constant? Time constant is 3 means, suppose this is the mu equal to 3 means, mu equal to 2 means the response will be like this. This is for mu equal to 1. This is mu equal to, this is mu equal to 2. This is mu equal to 1. That is closed loop time constant reduces, the response will be faster. So we designed 3 controllers for the same process. We designed 3 controllers for the same process and we check the, let us check the response. Here, we designed the controller for the process with the dead time. Let us check there. Here, what is the first part of the question? Design a Dhalin controller. The first part is you have to design for 1 by 3s plus 1. This is already we did in the previous class. The second part is e power minus 1.346 upon 3s plus 1. That we will check now. The third part is 1 by s plus 1 to the power 4. This can be approximated to, we have the Dhalin's design method for first order with the dead time. That's why 1 by s plus 1 to the power 4 can be approximated as e power minus 1.346 upon 3s plus 1. Therefore, if we design controller for this, this is also controller for 1 by s plus 1 to the power 4. No need to design for the third part. The same controller can be used here because this is the actual process. For that, we cannot find Z transform. So if you have dead time, first order plus dead time model of this, first order plus dead time model of this, we have. For that, we can design the Dhalin's controller. That can be used for this also. So now let us first apply on this, then we will check for this. Now we'll see the simulation for the three controllers. One is, what is the closed loop time constant? What is the closed loop time, open loop time constant? 3 seconds. So we can reduce the time constant in closed loop. That's why first we are assuming mu equal to 1. Second, we assume mu equal to 2. Third, we assume mu equal to 3. In this case, open loop time constant equal to closed loop time constant. The third case, first two are we reduce the time constant and we checked the we will check the response. Now here we have 3. The first one is mu equal to 1. What is the controller? Here you check the, here this is the summing block. Here we are giving set point. We are digitizing that continuous into digitizing by using 0 order hold we included. So after that, the controller, what we got, 0.6321 Z cube minus 0.4529 Z square. Then the Z term and constant term are 0. That's why we put the 0, 0, space 0, space 0. Denominator starts with power 4, 0.1959 Z power 4, 0.0155 minus 0.0322 Z square minus 0.1238 minus 0.0554 constant term. 4 terms are there. 5 terms are there, including constant term. 5 terms are there. We entered for mu equal to 1. Then we entered for mu equal to 2. Mu equal to 2 here. Mu equal to 2 is here. What you got is entered here. Then we entered another simulation. There we entered mu equal to 3. Mu equal to 3. Mu equal to 3 means what you got? 0.28 that we entered. So now we are going to control the fourth order process because we designed a controller for its model, first order model. For that we obtained the controller. That's why it will control fourth order process also. That we are going to controller. Here what we are giving, here the disturbance may be given here. The disturbance is given at the 40th second. Let us make it 0 now. Now we don't want to see any disturbance now, only regulatory response let us do. Let us make that is final value equal to 0. Let us make the disturbance equal to 0. No disturbance. We are going to do the regulatory response only. Regulatory response only. Now let us simulate. So you see, all settled. That's why the 4.93 for mu equal to 1. IAE, integral absolute error, is 4.93. For mu equal to 2, 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 ISA is 4.967 because it has a delay. We are assuming that the time constant is more. Mu equal to 1, mu equal to 2 means time constant, close to time constant is more. If you assume open loop time constant and closed loop time constant are equal, means further increase in IAE, 5.5. IAE also you see that mu equal to 1 means fast response. That's why 3.4. Mu equal to 2 means 3.7. Mu equal to 3 means 4.1. It increases. Now let us see the response all together. To see all the responses together. Sorry, here, this is all together. We see all the responses together. Yellow is for mu equal to 1. You notice that the response is faster. Rise time is minimum. Faster means rise time is minimum. For mu equal to 2, there is a slight delay in the response. Mu equal to 2. Mu equal to 3 means further delay. But there is no overshoot for mu equal to 3 because it has equal to open loop time, time constant. In open loop response, there is no oscillation. That's why in closed loop also there is no overshoot. You see that it has overshoot, but less absolute error, and ISA and IAE are lesser values. Settling time, almost all having the same settling time. All having the same settling time. But you have less ISA and IAE for mu equal to 1 and mu equal to 2 than mu equal to 3. So this you can check. Now let us check for regulatory response. For regulatory response alone, let us check. For that, what we have to do? We have to give servo response equal to 0. No change in set point. For regulatory response, no change in set point. Here also there is no change in set point. In simulation, 0 means it is at a nominal level. In simulation, set point 0 means it is at nominal level. It is for changes. Simulation is for changes. Now let us give the step disturbance at 40 seconds. So up to 40 seconds, it will be at 0. At 40th second, we are giving a step change in the input disturbance. Input disturbance is given at 40th second. Now let us simulate. Here also you notice that for mu equal to 1, lesser IAE and ISE. While compare with the other two cases, ISE is lesser. For mu equal to 2, you are getting 4.5. Mu equal to 1, 3.8. Mu equal to 3, you get 5.5. ISE also 1.6 for mu equal to 1, mu equal to 2, 2.2, mu equal to 3, 2.7. Let us see all the response together. All the responses together. Mu equal to 1 means yellow. Mu equal to 2 means that is close to time constant. 2 means time constant. 2 means blue. Close to time constant equal to open to time constant. That is 3 means red. You can see that better response for mu equal to 1. It reflects in ISE also. You can see all together also. That is also possible. For that, you have to give set point changes here. Now, let us check for The ideal case, the controller is designed for what? The controller is designed for 1 by 3s plus 1, 1 by 3s plus 1, e power minus 1.346. Let us enter that value here. Let us enter that value here. So we have to replace this by 1 upon 3s plus 1. Here 3 and 1 we have to enter. We have to include a dead time. After this, we have to include a dead time. We have to include a dead time here. Delay is 1.346. For that we designed the controller. So in that case, here also we have to include 1.346 dead time. Here also you have to include 1. So now let us simulate. Now we are doing for regulatory. Notice that for mu equal to 1, you have lesser IAE and ISE. For mu equal to 2, higher. The highest is for the open loop time constant equal to closed loop time constant. Let us see the response. Yellow is for you got better dynamics here. Better dynamics that because it is the ideal case. The controller for which it is designed is e power minus 1.436. That's why you can notice that ISE IA also lesser than while compare with for fourth order process. For fourth order process, what you got? You see there. It's not here. I saved as, so it's not available. Okay. But anyhow, if you compare, definitely for fourth order, you will get a higher ISC-IAU while compare with first order plus dead time, because this is the controller designed for e power minus 1.346 upon 3s plus 1, not for 1 by s plus 1 to the power 4. That is approximate model. Therefore, you can notice that ISC-IAU will be lesser for first order plus dead time model. That you can notice. Now let us do for servo response. Servo response, what we have to do? We have to make this equal to final value 1. Let us do both. Want of time, let us do both. So time is up. That's why let us do for both. Already some students are seeing the watch. Here also, it is the ideal case. That's why there is no overshoot. No, you notice that we designed for e power minus 1.346. What is the assumption we made? It is first order response. The assumption made is first order response. That's why no overshoot, because ideal case, that's why no overshoot at all. The response and assumption are same. What is the assumption made while designing the Dhalin's controller? It is a first order response with dead time. That's why the response also having the same, no overshoot at all. Because ideal case, already I told you that it is ideal case. That you can notice in the servo response. It is first order response. The regulator response also first order, but you can't understand that. There are no oscillation. But in regulator response, you can easily understand. Sorry, you can in servo response, you can easily understand. It is first order response. This first order response. And this is yellow is mu equal to 1, blue is mu equal to 2, and red is mu equal to 3. That is equal to. That's all about Dhalin's controller. That Kalman's controller you'll see in the next class. With that, 2 experiments will be over.